All right, I think we have enough people that we can start. So first of all, before we get into the actual content, I want you all to know that I'm an engineer and I don't make slides, so you should be very proud of me that this has all the right template and images and everything else. Would you mind giving me a round of applause? I really feel proud of myself for this. Thank you very much. My name is Ryan Barrett. I'm the lead on the App Engine Datastore. And this talk will explain basically how the Datastore works. There are a number of other great talks at this time, and so I appreciate you coming out and checking this one out. Feel free to check out the others later. They'll be recorded. Brad Fitzpatrick has one. Jeff Dean has another one. They're all going to be great. So before I start, I'd like to take a quick poll. Start off with an easy one. How many of you are familiar with App Engine? Awesome. How many of you have written App Engine code that uses the Datastore? Great. How many of you are familiar with BigTable? Okay. And have any of you read the BigTable paper or part of it? Cool. All right. So for you all, you can nap for the first 5-10 minutes. So here's what we're going to be talking about. I'm not going to give you any best practices. If you're here to find out how best to use the App Engine Datastore, you'll be able to figure it out, but I'm not going to tell you. I'm not a web app developer, and we have some web app developers on the team, but there are a lot more of you than there are of us on our team, and collectively you all have way more experience and expertise writing web apps. And so what I'm hoping I can do is explain how the Datastore does work, give some examples, and have you all kind of infer from that. I just realized I had some housekeeping that I didn't get to. All the standard stuff, if you can turn off cell phones, that kind of thing. There are informal birds of a feather areas starting immediately after the breakout sessions at 5:30. And make sure you stick around for the after hours, the party today, starting at 6. It'll be where the keynote was. All right, back to the content. Having said that, there are a few other App Engine talks that do get into best practices. Brett Slatkin gave one earlier today at 1:45, and again, that will be taped. And Rafe Kaplan has one, I'm not sure when it is, but it's coming up. So they will give you a lot more. What I'm going to be talking about is BigTable. I'll give you kind of a thumbnail overview. The App Engine Datastore is built on BigTable, which is a piece of our infrastructure. The entities table, which stores your actual entities, how queries on the App Engine Datastore work, and how we use different indexes to serve those queries. And I'll get into details about a few of the specific kinds of indexes. And finally, entity groups and transactions, how we make writes transactional, and how we shard across your data. So one more poll before I get too far into this. I have a lot of content here, more than I'm going to fit in an hour. I kind of need to do the BigTable and the entities table parts for you to understand what's going on, but queries and indexes and transactions and entity groups are interchangeable. So who really wants to know how queries work and how indexes work? Okay, there's a chunk of you. Who really wants to know about transactions and entity groups? That's true, he did. It's a good point, and they're about even. So I'll start going through the queries and indexes at the point of that. I'll start going through the queries, and if I get through it, we can talk about transactions too. So, here we go. I knew it wouldn't last, those pretty slides. So BigTable is what we use for structured storage. It's this word in the middle I got cut off. Google is really good, or has a great track record of dealing with unstructured data. So if you think about search, we pull in web pages which are basically arbitrary text with some formatting and some elements. HTML has some structure, but it varies so widely across web pages that we can't depend on much. And I'm ahead one. Come on. Okay. So BigTable is what we call structured storage, which is much more like a relational database. You have a schema. You know which columns are in which tables. You You have types for your columns. You know some are ints, some are strings, some are floats, that kind of thing. BigTable is designed for that. It's designed to be scalable, which is obviously the key, and which is one of the things we push on with App Engine. So BigTable is not a bunch of things you're familiar with. It's not a traditional relational database like MySQL or Oracle. It might be obvious, but it's not what we call a sharded database, where you partition your data horizontally. You say, okay, I've got 1 billion rows. I'm going to take 10 machines and put 100 million on each one. And they're all going to have the same schema, be running the same database, and I can talk to one or the other. We use that at Google, and a number of other companies use that too. BigTable is not that. It's not a distributed hash table, which is some of you might be familiar with. It's a decentralized set of machines that you talk to any one of them, and it won't necessarily have your data, but it'll know where to go to get it, which other machine might have it. Those are great, but BigTable is not that. What it is, it's a sharded, sorted array, and so this slide will kind of help. That's what I get for testing on Linux and then having to run on Windows. Apologies for the slides. So in this example, you see, assume that red is one machine, green is a second machine, and blue is a third machine. We have this array, this two-dimensional array of data. Each row has what we call a row name and a set of columns. The row name is what we sort our data on. So you'll see, obviously, it goes in order A through Z. And we split up the rows across machines. So that's what we mean by sharded. So the operations you get with BigTable, standard read and write individual rows, read, write, and delete, so your CRUD operations. Single row transactions, so you can read a row, do some operation based on it, and then write it back atomically, for example, increment. And you have scans, which you can either scan based on a prefix or a range of row names. So for the examples here, obviously, say you want to read B, you're going to pull out that individual row. Same with writing B. BigTable knows where to go to that individual row. Single row transactions, say you want to read B, operate on it, write it back. So X here is the data, and so there's some modified version of X that depended on the original value. Scanning, this is the magic. This is what we really like, and our bread and butter for doing queries, for example. There are two kinds of scans, as I mentioned. The first is based on a prefix. So you say, give me every row that starts with this. In this case, our prefix is B, and so it's going to give us all the rows that start with B. This is efficient. So one thing you can think of this is it's a constant number of disk seeks, which we care about. It just starts at the first row, and then it's going to scan through all the rest, and they're physically contiguous, which means that it only had to seek to the beginning, and then you get all of your really fast disk bandwidth, reading in all the rows that are next to each other until it hits the end. Same with range scan. So you say, I want to start at this row and end at this row. Here you want B through D. Same thing, physically contiguous, very efficient. So that's BigTable in not quite one slide, more like 10 slides. We're going to move on to the entities table. So we have a single table that stores every entity in every app in App Engine. That's what we call the entities table. Like I said, it's the primary table, stores all the entities. It's generic. So you, in the Datastore backend, you don't have to tell us your schema. We're going to store whatever you give us. You can change your schema on the fly. You can add things, remove things. We're OK. The row name we talked about. So in this table, this BigTable table that stores entities, the BigTable row name is based on the keys of your entities. We don't tend to use columns too much in App Engine. We basically have one column in the entities table that stores every single entity serialized down to a single string of bits. So we don't do much in terms of querying and filtering and sorting in the entities table. So keys, entity keys, are based on what we call parent entities. And most of you, if you've written an App Engine app, chances are you might not have even needed to use parent unless you tried to write transactions. So if you create an entity without a parent, it's what we call a root entity. It has no parents. Entity's key is based on the root all the way down to the entity in question, following the parent-child relationships. So pull up an example that'll help a little. Say we have 3 what we call kinds. They are subclasses of db.model. Grandparent, parent, and child for kind of ease of use here. We're going to create 3 of them, Ethel, Jane, and Timmy. And Ethel is the grandparent, Jane's the parent, Timmy's the child. Oh, and this is just ugly. This is what these keys are going to look like. So the first key is Ethel. She's a root entity. She doesn't have a parent. So her key is just her kind and her name. Jane's parent is Ethel. So her key is first Ethel, then Jane. Finally, Timmy's parent is Jane. So his key is Ethel, Jane, Timmy. It starts at the root all the way down. Here are some more examples. You'll note that they're ordered again by key. And so the key, the important thing here is the key, this whole chain from root down to your entity, goes directly into the BigTable row name. So the entities table, it's ordered by key. If you think of this as kind of a path down the tree, the parent-child tree, Alice, it comes before Ethel. So all of her children and all of her children's children will come before Ethel and all of her children. And then we have Frank and so on. And within Ethel, you'll see that there are, I don't have this in this example, but if Ethel had another child, say Bob, Bob would come before Jane. And Bob's children would all be next to Bob before Jane. So you can see how key kind of determines locality and where entities are physically located in the BigTable. So that's BigTable and the entities table. Any questions on this stuff specifically or clarifications before I go on? Yeah.
So if you decided that Timmy you put him as a child of Jane, you don't want that anymore, you want Timmy to be somewhere else, can you move him?
You can't change an entity's primary key. It's fixed once you create the entity. You can delete Timmy and create a new Timmy somewhere else that has a new primary key, and you can move all of his data. But you can't change a primary key in place. Because yes, absolutely. So the only way to reparent an entity is to delete it and recreate it. And this is because we're physically under the covers. The row name is really a BigTable row's identity. It's how it knows who it is. And so if you want to change the row name here, the key, it's going to be a different row. And that's what we care about if we're working on top of BigTable. All right, so moving on to queries and indexes, this is where it gets interesting. Working with entities, reading a single entity, writing a single entity, pretty straightforward. You know the key, so you know where it is in BigTable, so you know exactly where to go to get it and put it back. Queries, when you want multiple entities and you want to filter and sort, a little more interesting. So queries in App Engine, what you can do is you restrict by kind first, and kind is synonym for a table if you're working in a relational database, basically. You can filter on properties and property values. Properties correspond to columns in a relational database. You can sort on properties. So you can say, okay, give me all the stuff in this query, sorted by this property, sorted by age, for example. And you can say, I only want entities with this ancestor. And this part is interesting. Ancestor uses the parent-child relationships we talked about that go into the key. So Ethel, for example, if you said, give me everyone who is an ancestor, who has Ethel as an ancestor, it would give you Jane and Timmy and William. Right now, you also have to specify the kind, so you couldn't say that query. You could only say, give me all parents, or give me all children with the ancestor Ethel. Similarly, you can use a parent or a child itself as an ancestor, as you're not limited to the root of the hierarchy. Here are some example queries in our query language we call GQL, or GQL. It's a subset of SQL. It's a very small subset designed just for queries. And it kind of has some extra stuff you'll see with the ancestor restriction. But examples here, you see we use where for filters. We use order by for sorting. And ancestor is a special kind of clause that we use to specify ancestor restrictions. So our indexes, we have a few dedicated BigTable tables for our secondary indexes, which we use to serve query results. In a nutshell, what an index is the same as indexes in relational databases. They're ordered a little different. They're organized a little differently, but they do the same thing. Basically, they map property values and optionally ancestors and kinds to entities themselves. Specifically, each row in an index has what we call the index data, which is one or more properties and the kind and maybe the ancestor. And it also includes the entity key, which again is the BigTable row name. So we don't have the entire entity in there because an entity might have lots of index rows. But we know where to go to get it. So scanning indexes. Again, when I talked about scanning BigTable, scanning in BigTable, this is what we use all the time. And this is how we're going to build our queries, because BigTable doesn't let you do any of these kind of high-level operations, greater than, less than, equal, sort, order by, that kind of thing. All you get is scan. So we need to be able to convert queries to scans. And so here, what we're saying is we want scans that tell us exactly what the results are. We don't want to filter in memory. We don't want to sort in memory, not even a little. If your app has 10 million rows, you might think that by doing some of the filters, maybe the first few, we can narrow it down enough that we can do the rest in memory. Or maybe we do the first one. We don't know what your app looks like. We don't know what your data looks like, what shape. We use the word shape a lot. We don't know how your data is shaped. So we have no idea if we apply some of your filters or maybe all of them. We don't know how many results are coming back. So if we have to filter in memory or sort in memory, we might end up needing to pull in 1 million rows. And we have burly machines with a lot of memory, but if you have a popular app, and we hope you do, the results might not fit in memory. So we can't bet on that. We can't, not even a little. So again, as I said, the goal of queries in the App Engine Datastore is we want to convert a GQL query or a programmatic query you build up to an index scan, and that word there is dense. We want it to be what we call dense. So every single row in the index that we scan, we want to be a valid result, and we want it to come in the right order so that we can just scan, go fetch each of the keys, go fetch each of the entities the index rows point to, and give you the results back, and not have to think anymore about it. So the first task of query planning is picking the right index. The second is computing either the prefix or the range to scan, because that's all you get with BigTable. It's either prefix scan or a range scan, and then run it and fetch all the results. So the first index we have is the kind index. So this is serves queries, very simple queries. Give me everything of this kind. So this is what the index looks like in BigTable. So again, we have the index data, which we talked about before, is everything that tells us, or everything that we want to know about that entity for this index. Here, all we want to know is which kind it is. And so, as you see here, each row, that's what goes in the BigTable row name. And so the row name has both the kind and the key. And you might ask why the key is in the row name, and we use that for a number of internal reasons. But in the index tables, everything's in the row name. We don't have any columns. We don't really need them much. So here you can see they're organized by kind. And if we were to run this query, we'd say, okay, we want everything that's a grandparent. We know how to do that. We just say use the prefix grandparent and scan based on that. And we're going to start at the first grandparent row, go through to the end, and that gives us Ethel and Fred, which were our two grandparents. And so that's how we plan this query and go take it from GQL down to a BigTable index scan. And so you see the keys, Ethel and Fred. Before we actually give you back entities, we need to go do BigTable reads, one for each of those rows, and pull out the actual entity for Ethel and Fred, and give you back those. But as we said before, this is a dense index scan. Everything in here is a grandparent. And so we know that we're not having to filter in memory or skip over a bunch of results that didn't match. The kind index is pretty simple. The single property index gets into the meat of query planning and the data store. So as you might have guessed, the single property index serves queries that operate on a single property. That might be a single filter. It might be a single sort order. It might be multiple filters and a sort order. As long as it's on one property, we can get to a scan that will, a dense scan that will serve exactly the results you want in exactly the right order. We have two single property index tables, one that stores the property values in ascending order and one that stores them in descending order. We use them for if you ask for a sort order on a property and you ask for it ascending versus descending respectively. So here's what the single property index looks like for a few parent entities. Or this is a chunk of it. This is not the whole thing, but it's a horizontal slice, I guess you would call it. So the index data is the kind, again, the property name, and the property value. So here you see all of the index rows for the name property, and you see some of them for address and title. You see, obviously, we have a number of different pairs with different names. The name property values are ordered because you look at, they all start with parent name, and so the next thing that the BigTable row name is going to be sorted on is the property value, which is the name itself. In this index and in the composite indexes, which are coming up later, I'm omitting key from the end of the index rows, but just remember that there's a key here, and so every time we do a scan, we got to go fetch entities. This is the same index. It's descending, so you note that it's the same values, but in the opposite order. So if we were to serve a query that asks to order by name descending, this is the one we would use. So here's an example query. Give me everyone, all parents, where name equals John. Equals filters, again, similar to the kind index, we can convert to a prefix. So we say we know the kind, it's parent. We know the property name, it's name. And the value is John. So we know exactly the index data we want, parent name John. So this scan, this prefix scan, this is what we call it, the prefix is fully specified. So BigTable is going to know to scan exactly that row and no more. Sometimes there might be multiple people named John. In that case, you would have multiple index rows with the same index data. They would be differentiated by key. And so this is one reason we need the key in the row name, because we want each of those rows to be in there, but they can't have the same row name because that's unique. So the key is always unique for a given entity. The next query we looked at was select star from parent where, or order by name descending. This is one I mentioned before. We're sorting on a descending property, or sorting descending on a property, so we know we want to use the descending index that we looked at before, which is the same thing, just has the property values ordered descending. There's no where clause, just an order by, so we don't care what value name has. But we know we want to use name in the prefix because sort orders in the App Engine data store imply existence filters. If you sort on a property, you will only get result entities that have a value for that property. So given that, we say, okay, we know the kind, we know the property, we got the parent name prefix. We're going to scan with that prefix, give me every index row that starts with that. And so you see the scan goes through in the right order because, again, it's descending index on name. Finally, this one's a little more interesting. This one, you might do this if you had a directory and you wanted to show everyone whose name starts with B. So this is the B page, for example. And you want to sort them by their name. Here we have inequality filters, greater than, less than, that kind of thing. So we want to, we can't use a prefix for those. So we have to convert those instead to a range and use a BigTable range scan. The order by is ascending, so we know we want to use the ascending index. And the range is, we look at the inequality filters and say, okay, based on the direction, its ascending index, our range starting point is B. That's the greater than equals. So we know we want to start at B, or specifically we want to start at parent name B. And we want to end at parent name C. B is inclusive, and C is exclusive, based on those operators. So this scan, as you see, starts at B. There's no parent name B row, so it'll start at the next row, the next row after that, which is Bob. Bob is before parent name C, or would come before parent name C if that was in there. So it says, okay, I got Bob, I'm going to return that one. It'll keep going. Does the same check with Brad. Brad's less than parent name C. So that returns 2. Chelsea is greater than C. All these comparisons are effectively lexicographic. So it says, nope, Chelsea doesn't match. I'm done before Chelsea. So you get back Bob and Brad, who are the 2 names that start with B, ordered by their name. So that's the kind index and the single property index. Are there any clarifications on that stuff before I move into the composite indexes? Okay.
How do you deal with an inclusive? If you're trying to get the inclusive and you have a deceiving, just your range only showed an exclusive for the ending point.
Mm-hmm.
Is there an inclusive as well?
Yeah. So we support greater than or equal, less than or equal. Does that answer the question?
Yeah. I just see a syntax for how that would be.
Oh, yeah. So I haven't included the full GQuil grammar here, but yeah, we support all 4 of those operators. Yeah. Anything else? Sorry?
How would I find people
who forgot to enter their name? You wouldn't. There are a few options. You could, in your form, you could require that they enter a name. You could store an empty string for their name, or you could store none. There are lots of options. It's kind of out of scope of the talk, but if an entity doesn't have a property or it doesn't have a value for a given property, you're not going to see it if you filter or sort on that property. Did that answer the question?
Yeah, that's what you said before.
Yeah. Yes, it is somewhat surprising. In relational databases, there isn't really a corollary for not having a value for a column. It can be nullable or not nullable, but you don't have the same implications for whether you get results back or not. So we'll move on to composite indexes. Composite indexes are the ones you define yourself in index.yaml. If you've written an App Engine app that uses the Datastore, chances are you've at least seen index.yaml, even if you haven't had to deal with it yourself. Composite indexes serve queries on more than one property, or queries that include an ancestor. These we build on demand, because if we were to build every single index for every combination of properties, that kind of gets really big really fast. That's a combinatoric explosion, and even us with lots of disks and lots of machines might get too much. So we have to ask you for help at that point to tell us what queries you're going to run on multiple properties, and let us build the indexes for those when you tell us. Luckily, the SDK generates these automatically based on the queries you run, so usually you don't actually have to tell us. You just have to run it in the dev app server first, and then we know based on that. So here are some example queries, obviously. There's one that filters on 2 properties, first name and last name. One that filters on first name and sorts on last name. And one that restricts to a specific ancestor and sorts on a property. So say you have this index in your index.yaml. It's on the parent kind and has last name first, first name last. This is what that index would look like in BigTable. You notice the main difference from single property indexes is that we don't include the property name. You gave us the definition, so we know which properties are where. So to save space, we only include the values. Like before, it starts with the kind, then you have the value for each property, and then the key on the end, which I'm omitting for simplicity. So the algorithm for planning a query, taking a GQL query and converting it into a BigTable scan, there's a little more to it for composite indices because we have to go through each property and possibly the ancestor and figure out the right prefix or range. Again, similar to the other indexes, the kind comes first. Then if there is an ancestor, the ancestor comes next. We had the equals filters, properties for equals filters after that because we know the value, and so we can continue constructing this prefix. Finally, if there are inequality filters, those, again, like before, we need to use a range scan. So we're going to take this prefix we've built up, convert it to start and endpoints for this range scan. We're going to use the prefix and then tack on the values for those inequality filters. And afterward, I'm missing a bullet point here. We add on, we check that. So if you have sort orders, we're going to want those to come after so that the results you do get in this dense scan are sorted. So here's an example of the first query we looked at that has two filters, two equals filters. So we're going to start with kind again. We're going to say, OK, we got a couple equals filters. The first property in the index is last name. So we're going to go take the equals filter for that and tack that onto the prefix. Next property is first name. We're going to go say, OK, we have an equals filter for that, tack that onto the prefix. And so the prefix we get is parent Barrett Ryan. Tell BigTable to scan that. Similarly to before, this prefix is fully specified because this is the entire index data. So here again, we only have one entity, one matching result. We might have had more if there were multiple people with my name, and there definitely are if you Google my name. I'm far from the top. So that's the first query that would use a composite index and how we plan it. Honestly, this is one of the easiest ones. They get a little trickier. This one has a little more to it. There's an equals query on last name and a couple inequality filters on first name. Like before, start with parent, the kind. Last name, we say, OK, there's an equals filter. We start building up a prefix. Parent Smith. Smith is the property value for the last name equals filter. When we get to the first name property in the index, we say, OK, it has inequality filters. Now we convert to a range scan. We got this parent Smith prefix. And so for the value that we're going to use in the start and endpoints, we know the index is ascend. Let's see, this is descending. The index is descending. Is that right? No, sorry. The index is ascending on first name. So we take the greater than equals, again, similar to last time. We say the start point is going to be parent Smith B, inclusive because it's greater than or equals. The end point is parent Smith C, similar to last time, exclusive. And so that gives us Bob and Brad. And this could be the same directory page. Maybe it's in a genealogy app, so you know the last name. So ancestor queries. In your index.yaml, when you have an index that serves an ancestor query, it has an extra part, and it says ancestor yes or no. And that just tells it whether to include the ancestor, obviously, in the index. So here, with this index, kind comes first again, then ancestor before any of the properties, then first name, which is the only property. If there were more properties, they would continue on until the end. So you'll note that just like usual in BigTable, it's sorted by the row name. Kind is all the same, so sorting falls through to ancestor. David comes before Ethel, comes before Fred. And within Ethel, first name is going to be how those rows are sorted. So with that index, we could serve a query like this where we say, I want only people who are descendants of Ethel and sort by their name. So like before, start building a prefix. Kind is the first one, parent, obviously. Next is ancestor, and ancestor we treat kind of like an equals filter because we only want people whose ancestor equals ethyl, even though we have kind of dedicated syntax for this. So we say, the next prefix is ethyl. And finally, we look at the next property. We want to make sure it's mentioned in the query, because otherwise it's not going to match. And right now, we do exact index matches. So the reason for this actually is kind of a tangent. But to your point before about sort orders implying existence filters, sorting on a property requiring that the entity has that property, if we used this index for a query where ancestor is ethyl and no sort order, the index itself will only have rows for entities that have the first name property. So if we were to use this index, it would filter out unintentionally all of the entities that didn't have first name. And you didn't specify that as a sort order, so that would be incorrect. So we have to make sure that the index matches exactly. Here, sorry, question? So it's ancestor, not parent, because ancestor matches if any ancestor up the chain, any of your entity's ancestors up the chain is that ancestor. So it could be the parent, it could be the grandparent, it could be anywhere up to the root. Yeah, and your second question I missed. Yeah, I'm sorry, I'm not quite following. Oh, yeah, okay, so I see. So if the ancestor you asked for was not a top level or a root entity. Yeah, so for simplicity here, I only included top level entities, but ancestor indexes also include children of top level entities and ancestors that are further down. So we index each ancestor for a given entity. There were a couple different ways to do this, and there were trade-offs with each, space versus time, some classic trade-offs. And so we went with that solution, and there were others, but it's worked out well so far. Did that make sense? Did it work? Cool. Yep, so that was this example. Prefix is just parent ethyl. We don't include first name because we don't care what value they have for it. We just want to make sure they have a value, and we want to make sure it's in the index so it's sorted by them. And since the prefix is parent ethyl, we know every entity or every index row has the same value for both kind and ancestor. So the only values they're going to differ on are first name, and so we know that's how the results will be sorted. All right. Yeah.
Is it possible to run a query if you don't have an index for it?
So we can serve a number of kinds of queries off of only the single property indexes. Not everything, but a number. You can do a query with an arbitrary number of equals filters on one property or on multiple properties. You can do, let's see, I think you can do a property with equals filters and an ancestor restriction. And I didn't include that in this because there's a little more to it. If there's interest, I can add it to the slides and when we post them later. What we can do is do multiple scans and basically merge the results, effectively do an intersection. So with certain kinds of queries, you don't need a composite index. It's not entirely intuitive which kinds of queries those are, but if you just use the rule of thumb that if you just have equals filters, you can do anything you want and you don't need an index and index.yaml, that'll get you a long way. All right, so we have time for a little on transactions. Before I do that, any clarifications on queries and indexes? Yeah, absolutely. So BigTable just treats the row name as an opaque bit or byte string. It doesn't care what you have in there. You can specify any number of bytes as the prefix. we don't expose a built-in way to do string prefix queries for you. So if you wanted to say, give me everything where first name starts with, BAT. There's no obvious way to do that. We kind of hacked it in here, for example. Say give me everyone whose first name starts with B. There is a way to do string prefix queries in the docs, and I don't know which part of the docs off the top of my head. It might be in the queries and indexes page. You can effectively say, give me everything greater than or equal to the prefix, and less than or equal to the prefix plus the maximum UTF-8 character, or the maximum UTF-8 code point. And that effectively does what you're looking for. Any other questions, clarifications on queries and indexes and query planning? It's a great question. This is something. Sorry, yeah. Are you charged for your indexes? Are you charged for the space they take up on disk? So I'll talk a little bit about that. It's technically I should punt to a PM, but I always like to shoot my mouth off, so I'll see if I can take a stab at it. One of the things that people who build developer platforms have found is that when you charge for something, engineers tend to love to solve problems, and optimizing to pay as little money as possible is a great problem to solve. It has a really well-defined success criteria, and you can if you think about it, you can find great ways around pretty much any pricing structure. And so if we were to charge you for your composite indexes, for example, for the space they take up, we expect that we would see at least some people jumping through hoops to not have to use composite indexes. And there are definitely ways to do it. We want to encourage people to use the stuff we've built because it's helpful. Obviously, it's easier than building a bunch of stuff yourself. And so we know that if we were to charge for composite indexes, it would encourage people to go to extra trouble to solve problems that have already been solved. So we'd like not to. I don't know that we have that we've announced that officially, but we prefer not to. The single property indexes apply to everyone equally, and so the cost for storing entities will have some fixed overhead based on the encoding in BigTable, possibly indexes, other stuff, but that will be fixed and not based on the indexes you define. I see a gun in Pete's hand over there. We'll see if you let me get away with that. Sure. So, like we said before, we only want to do what's called these dense index scans. We don't want to try to filter or sort in memory. So if there's no index for a query and we can't handle it with the single property indexes, we give up. We throw an exception. And if any of you have seen a need index error, that's what's going on. We recently actually pushed a small new feature to need index error where it tells you the index that you need. Which helps. Almost always, if you have run a query in Dev App Server, it generates the index you need. So often what we find for that, we find people hit that if they just didn't hit that query in Dev App Server before they deployed. Yeah?
The question earlier about not being able to search for rows where a property has no value, would the workaround to that if it's necessary to find an entity that has a value isn't the property, is to search on parent properties, and then basically your application functions to see if the child property has a value.
I didn't entirely follow. There might be something there. So parent and child are not properties. They're, or maybe I'm just, you can, oh, you can definitely store an empty string. You can store, not, sorry, the question was, you know, is there maybe a workaround to searching or to querying or, for entities that don't have a given property? You can store empty strings in string properties. You can store none, which is distinct from the empty string, and you can not store anything. So if you use db.model and define your schema, if you don't provide a value for a given property, I believe it stores none. So none is a valid value, and if a property has a none as a value, if you sort on that property or query on it, you will get those entities back.
So it sounds like that last question is really for the expando kind of model.
Sure. Yep.
Or this is an extra field that isn't defined in the model.
Yeah. So yes. So if you are using the schemaless models, so the question was that it's oriented more toward db.expando than db.model. And if you're not familiar with these, I would encourage you to read the docs. Expando basically lets you store schemaless data, treat entities as pure property value or key value bags. Yeah, so that's where you will run into it. And it's honestly just a fact of life with the data store right now. There are workarounds. If you know what properties you're going to have ahead of time, then again, you can define them as static properties, and you can have them stored as none. In your code, you can go through all the properties that an entity has with the properties method on model and expando. And you know, before you save it, before you put it, let's see. Now, you would actually need to know which properties you were expecting. But if you know the properties you're expecting, then you can go through and set none on all of them. But yeah, it is a quirk of the data store that that sometimes happens when you're working with something that's schemaless. I'm going to see a couple more questions. I'm going to see if I can get through part of the transactions slides. We have 11 minutes, so I'll time myself, and I'll try to leave room at the end for a few more questions. So the transaction model for the data store is that all writes, puts, and deletes are transactional, whether or not you explicitly wrap them in a transaction. We use journals. We journal all of the writes, and journals are time-stamped, and this is basically how we implement this. In each row, we have the last few versions of an entity. They're all time-stamped, and we use what we call optimistic concurrency instead of locking. So instead of locking a specific row or an entire table, we have everyone try to write, and then at the end, right when they commit, they say, okay, did anyone else jump in the middle? And if so, they have to give up and retry. We find that this helps throughput a lot compared to traditional locking designs. So I'm going to jump straight into an example. So here's the example: is just putting a single entity. And even though it's not in a transaction that you wrote, for example, we still effectively wrap in a transaction. So here you see this is a row in the entities table, and I've added a few parts to it. The parts you remember from before are the entity key, A, and the entity data, which I'm representing as X here. In parentheses is 3 o'clock over there. And so that says this version of the entity was written at 3 o'clock. The extra stuff is a transaction journal, which stores basically all of the data that was written to this entity, or all the recent data. We garbage collect this. And the timestamp, the timestamp that the entity was last committed, so the time that all of the changes were applied, and it's fully up to date. And so here, again, it's 3 o'clock, so this is steady state. This entity hasn't been written to for a while. So if we want to write a new value to A, the first thing we're going to do is do a read on this row in the entities table, pull out this committed timestamp, say, okay, the last committed time was 3 o'clock. If we were to do, if we were in a full-fledged transaction that you did some gets and puts in instead of just a single put, all of your gets would use this timestamp. So they would know to see a consistent view of the data store. The next step here is to write the journal. Basically, we're basically telling the data store what we're going to do before we do it. So say it's 345, and we want to write new entity data, say it's Y. So we write this to the journal. We say, okay, the timestamp right now is 345. We're going to write Y to A. Get ready, we're going to do it. The next step is we take everything in that journal and apply it. That basically just means writing out to the actual entity data. So obviously, we have the new entity, Y, and we have the timestamp that it was written at. You'll note the committed timestamp is still 3 o'clock. We haven't committed this transaction yet. So if another request was to come in and issue a GET, it's going to look at that committed timestamp and say, oh, okay, the last commit was at 3 o'clock. I'm only going to read that because that's the only thing I know that is complete and that has been completely written. If this BigTable tablet server was to die halfway through the entity writes, or if one of our servers was to die halfway through, we would avoid having other requests read that partial data because they wouldn't be looking at the 345. They'd only be looking at the 3 o'clock, which they know is safe. The final part of the transaction is committing, and as you might have guessed, that consists of updating the committed timestamp, the last time that we know it was complete. So we only do this after we've written out the full new contents of the entity and we know it's in there. So I'm not going to have enough time to get through the extended example, but if you were to imagine that, let's see, let me try to retrofit part of that later example into this one. Yeah, so if you remember when we went back and at the beginning, we read the original committed timestamp. We said, okay, we're starting our transaction. We know the last time this entity was written was 3 o'clock. Go through the end. What we're going to do before we write out the new committed timestamp is in a single BigTable row transaction. Remember that BigTable lets you do transactions on a single row. We're going to read this row again. We're going to look at that committed timestamp. We're going to say, is it what we started with? If it's changed, we know some other request came in and changed this entity out from under us. And we don't want to write our changes because they wouldn't be atomic. So if it was 310 or 320, for example, we would basically give up. We would roll back. Or we wouldn't update the committed timestamp. Future gets would look at that timestamp and they would say, we know that only this one is finished. Only this one has been atomic and fully committed. But in this one we were safe. No one else snuck in. So we can write the committed timestamp at 345 and say, okay, everything's set. Yeah, let's do this one and then I'll call it quits. If you were in Brett's Slack-in talk, I know he went through this a fair amount, so I'll just mention that what was obviously missing from that is transactions on multiple different entities. The way we allow that is what we call entity groups. So you basically tell us, this group of entities, I want to be able to operate on them in transaction together. And those groups are called entity groups. Right now they're defined by the root entity in that those parent-child relationships in the key. Every entity that is descended from a given root is in the same group. It consists of the root entity and all of its descendants. The journal and the last committed timestamp always live at the root entity. So the way we handle concurrency and contention, journaling, timestamps, all the stuff we showed before is you always look at the entity group root when you start a transaction and then when you're about to finish and commit. So that, and the journal that you write contains your rights to every single entity in your transaction. So even if they're in other rows, which they will be if they're not the root entity, the journal and the timestamp will always live at the root so that we can do single row BigTable transactions on that root. We can check the last committed timestamp and then update it when we need to. So that was transactions and entity models. Let me skip ahead to the end. Yeah, I lied. There are a few small best practices here. Keep your entity groups small. I know Brett mentioned this, but writes are effectively serialized per entity group because you're always hitting that entity group root or that root entity row for your journals and your last committed timestamp. If you have big entity groups, you effectively serialize all your writes through that root, which is no fun. Right now, if you have properties that you know you don't need to query on, and you're seeing puts that are slow, use text and blob. This is because text and blob are not indexed, so we don't have to write index rows for them. Finally, queries are pretty powerful. It's not full SQL, but you can do a lot. If you can, see if you can do what you need to do in a query. Generally, it'll be faster, and you won't get hit for CPU quota as much. So we went through BigTable. We went through how the entities table is laid out. We went through queries and each of the different kinds of indexes. And we went through transactions a little and entity groups. So I think I'll take questions here. I've got all of like 3 minutes.
I remember from the BigTable paper,
Mm-hmm.
full histories and peculiarities. Is there a way to access the histories of an entity?
BigTable, the row history is actually configurable. So most Google products don't keep full history. They keep some history, and it's garbage collected. So right now, no, there is no way to access that history for your App Engine data. Yeah.
Can you get at the timestamp and query on it?
No, no, sorry. Mm-hmm. Yeah, we are strongly consistent. Yeah, thank you. So why are we not eventually consistent like SimpleDB? The short answer is we do everything synchronously. We don't return from a put until your entity is in there, the committed timestamp is updated, and all the index rows are updated. So you'll see contention. Slow down your puts because we have to retry sometimes to get them in there without someone else sneaking in. And sometimes we'll return errors when there was too much contention and we couldn't get something fully written. So that's the trade-off. SimpleDB, with its eventual consistency, I believe you don't see contention errors and you don't see those kinds of errors, but the cost is that it's not strongly consistent. Yes. We have one, and we haven't exposed it yet. We would like to. It's not a high priority, but it's on our list. Mm-hmm. Yep. So that was another place where, in reality, it's a little more complex. There are a couple techniques we use to guarantee that different servers don't accidentally use the same timestamp and clobber each other. So it's not the full story, but it's enough to kind of get you started. No, sorry, go ahead. Full text search kind of thing? No. So you can do string prefix queries like we talked about, and there is a full text search module. If you search the group for full text, you'll find it. It's not as robust as we plan to provide eventually. It's a short-term hack. We plan to provide something much better, but it works in the short term. So offline processing is something we very much want to do, and that includes kind of large-scale data upload and download, that kind of thing. It's a big project, and so to do it right is going to take us a while before we get it out there. But that, along with more languages and billing, are the three big features, big projects that we're actively working on. Thank you all for coming. I appreciate it. Have a great conference.